You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
The Naked Scientist is back. Chris, you are with us this week, and we've just opened our lines taking our science questions on any subject. Chris is going to be answering all your questions. Chris, good morning.
Good morning.
My name is Mamokgethi. Chris, I'm so delighted to meet you. I've seen you at the Rand Easter show, and I've listened to you on the radio. You are so clever. And I want to ask, my nephew asked me to ask you this question. What did you study to be so smart? What is it? He wants to be what you are.
Well, I started off just doing medicine, and so I went to medical school, and in the middle of my medical degree, I did a degree in neuroscience, how the brain works, and then I did a PhD in virology and gene therapy, largely for the nervous system. Then I finished my medical degree. I worked as a doctor. I still work as a medical doctor. And also in the middle of my PhD, I started making science radio programs because I found it was a way of feeding my insatiable hunger for knowledge, because I could then legitimately, and say it was work, read everything that came my way and educate myself. So that's what I did.
Wow. You know, Chris, for some reason, I thought you studied physics, because I always say the smartest scientists are physicists. But clearly I was wrong.
It's certainly true that physics does explain a lot of how the universe around us, if not all of the universe around us, works. It doesn't explain the human condition. We still have bizarre human behaviour that defies explanation. But physics explains how the majority of what you see around you works. And the amazing thing, the real mind-boggling thing, is that the rules of physics that work here on Earth, you can go to the other side of the universe, and the same science is at play controlling how everything works. And so that's why it's an amazing thing. It's a science that scales. It scales from the very, very small to the scale of the universe.
Okay. We're going to the ad break now. Chris, we'll talk to you afterwards.
702 and Cape Talk.
The Naked Scientist.
You're back on the Friday stand-in with me, Mamokgethi Phakeng. We are now having the Naked Scientist, and we are accepting your calls. If you are in Johannesburg or Gauteng, call us on 011-883-0702 or 021-446-0567. You can also tweet me on @FabAcademic or Instagram @FabAcademic. We have the first question, and the first question is from Husna. Husna in Omonde. Hello, Husna.
Good morning.
Good morning. What's your question?
This question is for the Naked Scientist.
Yes, he's listening.
I enjoy natural science a lot. I'm in grade 9. So the question that I would like to ask is regarding to H2O, which is water. So in the chemical equation, H2 plus O2 will give you H2O. So what I've realized is that you have diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So oxygen is part of the diatomic elements. So I would like to know is that why wouldn't we write H2O2 instead of H2O? Why would we write H2O instead of H2O2?
Chris?
Yes, it used to confuse me as well, and I thought, why is magnesium oxide MgO and not MgO2? Because oxygen's O2. The reason oxygen atoms hang around in pairs, and instead of being O, they are O2, and we'll take oxygen as an example. We could also use chlorine as an example. In fact, why don't we talk about chlorine? Right. The reason is that atoms have a central nucleus which has got protons and neutrons in it. Those are the positive charges, and around them is a cloud of electrons, which are the negative charges, and there's equal numbers of electrons and protons in an uncharged atom. Now, the electrons don't just sit anywhere. They organise themselves into particular, what we call shells or orbitals, where they spend more of their time around the atom than in other places. And there are certain arrangements which are stable. And for reasons we don't entirely understand, the electrons like to hang around, or are considered to hang around, in pairs. And if you have an atom like chlorine, then what it's got in the outer layer of electrons, if you think about the structure of an atom, the outer part of the cloud of electrons, there's 7 electrons in one chlorine atom. Well, electrons don't want to be unpaired and on their own. They're lonely. So what chlorine does is it goes and finds another chlorine atom, and it forms Cl2, a diatomic molecule, because then the two share their electron that's lonely, and so the two get together and you've got a pair of electrons that are less lonely, but in order to make that sharing possible, they have to hang around as a pair. Oxygen does a similar sort of thing, and when these atoms react. So what an oxygen atom wants to do, it's got two gaps actually in its outer shell. It wants to share two electrons. So hydrogen comes in, it's got a spare electron, and oxygen's got a spare gap, so one hydrogen fills one of the gaps, one hydrogen fills one of the other gaps, and so you've got one oxygen in the middle, hydrogen, hydrogen, and that's why it's H2O. So the oxygen can make two of these connections to hydrogen, if you like. That's why you get H2O.
Fantastic. Thank you very much, Husna. Thank you, Chris. And we go to Jimmy in Cape Town. Jimmy, hello.
Hi, good morning. My question is, if you take a very strong magnet plate and fix it in front of the cars, could it help to stop head-on collision?
Oh, hi, Jimmy. Well, I suppose it could do, because as the magnets approximated or approached each other, then they would repel each other, and that would have a decelerating effect on the cars. But the thing is that the magnetic field obeys an inverse square law. What that means is that the field becomes, if you double the distance between one magnet and another, actually the strength of the field is a quarter. And so as a result of that, very quickly the magnetic effect falls off, and so your cars would have to get very, very close before they began to feel very much of a magnetic effect, and that means that there wouldn't be very much time for the deceleration to occur, because what makes a car accident a safe accident versus an unsafe accident is how fast you slow down. You can be doing 1,000,000 miles an hour, but if you slow down slowly, you're not going to do damage. It's when you slow down very fast that you do damage. So if you end up having to get so close for your magnets to decelerate you, you're still going to slow down very quickly, and that could do you harm. Now, talking of car accidents, I have to say, thank you very much to the people who wrote in last week. Paul asked a very good question last week saying, is it worse to drive your car into a wall, or is it worse to drive your car into another identical car going the same speed as you in the opposite direction? The answer I gave was suboptimal. I think I confused a lot of people, and I'm very grateful to those people who wrote in and said, here's a clearer way of thinking about it. Now, the clearest way of thinking about it comes from somebody actually on our web forum, on the nakedscientist.com/forum, who said, if you think about it in kinetic energy terms, one vehicle going one way, one vehicle going the other, they effectively have twice the kinetic energy. So if they slam into each other, there are two vehicles to share twice the energy, so therefore it's no worse to slam into another car doing the opposite speed, in the same speed in the opposite direction, than it is to just slam into a perfectly hard brick wall, because you're sharing the energy between two, and therefore it's still the equivalent of you driving into a wall. It's no worse.
Okay. Tabo in Soshanguve, you want to ask about planet or star called Canis Majoris?
Oh, yes. I would like to know from Chris, the VY Canis Majoris, is it a star or is it a planet? And would it fit in our solar system? Is that possible?
I don't know very much about that star, I have to admit. I believe it is a star. The answer is it's not in our solar system, because our solar system is the sun in the middle. Then there are the clutch of planets, the rocky worlds in the middle, which is Mercury, Venus, the Earth and Mars. And then you've got the gas giants. And then beyond that, you have dwarf planets, as we now relegate Pluto into that particular genre. And beyond that is the Kuiper Belt, with all these other interesting things lurking out there. And beyond that is the Oort cloud. Beyond our solar system, you're then looking at the realms of other stars in the Milky Way galaxy, and there's something like 100 billion stars in the Milky Way, so it's one of those.
Wow. Okay. Jeffrey in Cape Town, you want to talk about salt?
Yes. Hi, Chris. Chris, I've got a question. We've got a lady in South Africa called Suzelle. She does DIY programs. She says if you want to cool down cool drinks or beer quickly, what you do is you get a tap, put water in, add ice, and put the cool drinks in. Now, we all know that. But she says put salt in as well. I want to know if the salt would actually help it get colder quicker.
Right. If you put salt on ice, then the temperature drops dramatically. And this is well known, and the Victorians, in Queen Victoria's era in England, invented the idea of making ice cream by doing precisely this. If I take a block of ice and I take the temperature of it, it's about 0 degrees. If I put ice all over it, the temperature bizarrely plummets to minus 18 degrees centigrade. Why does it do this? Well, the reason is when you add ice to salt, the ice particles they get in the way of water molecules which are trying to rejoin the ice crystal. What do I mean by that? Well, when you look at a structure, if you've got an ice cube, then this is a whole load of water molecules stuck together. They have a certain amount of energy, and the energy is randomly distributed amongst all the molecules. This means occasionally, just by chance, the odd molecule will have enough energy, making it vibrate hard enough that it falls off of the ice crystal and wanders away for a little while, taking some of that energy away from the ice crystal. That means that the net energy in the ice crystal, and hence its temperature, transiently drops. If you put salt on there, the salt crystals, the salt, gets in the way of the water molecule trying to go back dynamically onto the ice crystal and give that energy back. So therefore, the average energy of the ice falls, and that's why the temperature falls. And this means if you put milk, sugar or beer in a bowl on top of ice covered in salt, then you will potentially be able to freeze the beer or the cream to make ice cream or very nice cold beer by making what they call an ice and salt sandwich.
Wow, okay.
Hello.
Hello, now we go to... Harold. Hello, Harold.
Yeah. Hello.
Hello, Harold. You can ask Chris your question.
Okay. Hi, Chris. Hello.
Hello, Chris. Are you there?
Harold, we're waiting for you to ask your question. Just go for it.
Sorry, I'll be as quick as I can. It's mainly a medical thing with... I've had sciatic a year and a half ago, and that healed itself on the spine, and I had an MRI then, and the last couple of weeks I've had a couple of MRIs and a brain scan and you name it, neck scan, and my knees, my legs, my buttocks are numb. I also had a epidural, what do they call it, a spinal block. And then, this was after having Polygam. I don't know if you know Polygam and cortisone. And now they don't seem to have an answer. The X-rays show that the back is, not the cause of this. And I cannot stand. I can't walk. I battle to lie and sit. Any suggestions, please, Chris?
Hi, Harold. Well, I don't do on-air diagnosis because I think that's dangerous, but I will comment generally on the sort of history you're giving us. Sciatica occurs when there is impingement of the nerves which leave the bottom part of your spinal cord, and they run out through very tiny holes in the spinal bones. These are called the foraminae. And as we age, and as tissues become saggier, then you can get impingement or squeezing of the nerve by build-up of bony areas and sometimes a collapse of bone. And when you squeeze those nerves, it then leads to the nerve transmitting the sensation of pain into the spinal cord. And so you believe that the parts of the body supplied by the trapped nerve hurt. This is referred pain. And about a third of the time, people who have this, it gets better spontaneously. About a third of the time, it doesn't get any worse. And about a third of the time, it gets better. So the majority of these things will actually, if you leave them alone and just take anti-inflammatories, they do have a very good chance of improving. Now, the reason that you may have numbness and things like that is because if you squeeze those nerves hard enough, sometimes they stop sending any signals at all. Worst case scenario, some of them may even die. And this means you lose the ability to sense from the area supplied by the nerve. You can also lose the motor nerve supplying muscles, because if those nerves are being squeezed as well, you won't be able to activate the muscles that those nerves would normally send messages to make you move. That may be what's happening in your case, but it's certainly important if you have got that sort of neurology, if you've got evolving weakness and sensory loss, then this does need a good sort out, and someone needs to look at why this is happening and find out what the source of it is, whether it is trapped nerves or something higher up in the spinal cord, and try and find out what's causing that so that the problem can be stopped, because you could reach a point where it will be impossible to recover the nerve function. If you damage these nerves so significantly, they may not recover.
Thank you very much, Chris. Chris, I have one last question for you. That dizzy feeling that you get when you stand up too fast, I get it sometimes when I wake up, and so I have to wake up slowly. What causes it?
Well, that's called postural hypotension. Posture, as in postural, meaning posture, when you go from a recumbent position to a standing position, hypotension, meaning low blood pressure. When you stand up, you are affecting the way in which blood is capable of returning from your peripheries, particularly your legs, to the right side of your heart. And the right side of your heart collects blood from the rest of the body, puts it through your lungs, and then sends it to the left side of your heart to be pumped back around the body, including to your brain. When you stand up suddenly, because the amount of blood being squeezed back up from your legs transiently drops going into the right side of the heart, this means that the amount of blood that can come out of the heart must drop, because if you put less in, less is going to come out. And this means that there's a very transient drop in the perfusion, the supply of blood to your brain, and also especially to your retina. And the retina has one of the highest metabolic rates in the body, and so you tend to see stars and feel a bit woozy until the compensatory mechanisms kick in, and what they do is they squeeze the muscles around the veins in your legs. They also squeeze the muscles in your legs, and they increase the rate of beating of the heart, and these compensatory mechanisms restore the normal flow of blood. And that means that your brain then stops suffering from a perfusion deficit and you feel normal again. But if this does happen, which is pretty common, it's important to know that it tends to happen in you, especially on hot days or if you've been exercising and you suddenly leap up, because you can faint and then you can hurt yourself. So it's important if this does happen to you, and it's more common in older people, and it's also more common in older people on blood pressure controlling medication. Very important to stand up slowly. So, do it in stages, arms on the side of the chair, push up a bit, stand up, and then slowly get yourself up to a standing position, and then you will actually reduce the risk of getting woozy.
Okay. Thank you very much, Chris. Thank you so much for answering all the questions. We're wrapping it up now. Thank you and enjoy your weekend.
Okay, thanks everyone. Take care. Bye.
Bye.